Well, I just made this little guide to help you study for the Unit 6 exam. And here are the concepts that, the vocabulary, the words, and so on. I want you to know what they mean and how to use them. What is energy? Energy is the capacity to make changes in your environment. If something has energy, it can make change. Work is when energy is being transferred from one system into another system through the application of a force. And of course, we've got an expression for work. Work equals the force times the displacement times the cosine of theta. Now look at what theta is here. Theta is not the angle of incline. Theta is the angle between these two vectors. Force is a vector. Displacement is a vector. If there is an angle between them that isn't zero, if it's whatever angle it is, even if it is zero, you have to look for it. Now, if the force and the the force vector and the displacement vector are in the same direction, the angle between them is zero, and the cosine of zero is 1. So you get all the work, you get all the forces contributing to the work. If the force and displacement are at a 45-degree angle or a 60-degree angle, then less of the force is in the same direction, so as the displacement, so you're going to have less work being done. What if the force and the displacement are at 90 degrees? Well, the cosine of 90 degrees is 0. That force isn't doing any work. Okay, so make sure you know how to use this. I'm going to test whether or not you know how to figure out what that theta is when I give you a problem and you have to figure out how much work is done by the force. If the net force is doing work, that will result in a change in kinetic energy. And this is the Work-Energy Theorem. Of course, when we actually did this, when we derived this, we found out the kinetic energy is 1/2 the mass of an object times the velocity squared. That's how you relate, the work done by the net force on an object to its velocity. Let's say you have an object at rest, and you apply a net force to it, and you figure out what the displacement is, and you figure out how much work was done by that net force. Well, the result of doing all that work is motion. But mv squared, 1/2 mv squared, this gives you the result of doing all that work. And we call that kinetic energy. And you can get all that work back. If something is moving, it can apply a force times a displacement equal to this amount of energy. So we can get that work back from something that has kinetic energy. Now, if I lift something up in a gravity field, if the mass of an object times gravity field times h, that's a gravitational potential energy, which I'm calling U sub g. If you still want to call it PE, which I think the book does, you can do that. This is what the AP test does, though, so that's why I'm using it. Elastic potential energy, 1/2 kx squared. What is that k? That little k. Ooh, I forgot to put it in here. That is called the spring constant, little k, and it's the force you need per meter of stretch or compression. And this is called the spring constant. So there's a spring constant times x squared. What else do you need to know? You need to know the definition of mechanical energy is just the kinetic energy plus the gravitational potential energy plus the elastic potential energy. If you're dealing with nothing but conservative forces, that is, the only forces doing work are gravity or springs, then you can say that the initial mechanical energy of the system will be equal to the final mechanical energy of the system. No mechanical energy will be lost. That means there's no friction, there's nobody adding to it. Is that my magnet thing right there? Okay. Now, if you do have a non-conservative force doing work, now that's like an applied force. If you push on something and you give it speed, well, you just transferred energy out of your system and gave it to the mechanical energy of the thing that you just pushed. So you added to the mechanical energy of the system, delta E. That's a change. Your final mechanical energy will be greater. Now, what if you have friction? Something is moving, but there's friction, and it's slowing it down and turning all that stuff into internal energy, or the thermal energy. Well, then that work done by friction will be negative. You'll have a loss. E final minus E initial will give you a negative value. Just like I think you worked a problem like similar to that today. Now, power. Power equals work over time, or the energy transferred over time. That's joule per second, which is a watt. Also, if you apply a force times the velocity, that'll give you the same. It has the same units, and that'll give you the power produced by like an engine or something. If you're driving down the road and your car needs to apply 400 newtons at a speed of 25 meters per second, you just multiply those two together, and that's how much power the engine is putting out to keep you moving. Okay, so you'll have a problem like that. So now I made this little, I call it a quantity chart right here, where I put the quantity name, the variable we use, and some notes about the units that we use. And notice that work, kinetic energy, gravitational potential energy, elastic potential energy, mechanical energy, we use joules for all of them. Now, power is the amount of energy being transferred per unit time, joules per second, which is a watt. And of course, spring constant K, which we use in the elastic potential energy. Now, looking at the kind of problems that you're going to be doing. One of the things that you'll need to know graphically is that if you graph force as a function of position or displacement, doesn't really matter. If I give you something where it kind of ramps up like this, I don't know, classic kind of trapezoid thing, the area underneath your graph, we said, represents the work done by this force. And so I'm going to give you a graph. So when you look at the problems that I gave you for the take-home test, that's what I'm going to give you problems very similar to the take-home test. Let's go ahead and look at it. I could give you a problem. I will definitely give you a problem where there is a force and a displacement, and they're not necessarily parallel. And so you're going to have to figure out how much work is done by the forces. And very similar to this, like how much work was done by the normal force, by the gravitational force, as this thing moves to the right. Remember that cosine theta, if theta is 90 degrees, cosine of 90 degrees is 0. That means that no energy is being transferred to or from the object that's moving because of those forces. But this force, look at this 35 Newton force, right? It's a component of it is the one that's accelerating it to the right. So then you can have a conservation of mechanical energy problem, which basically this is if you squish in a spring and you fire a dart gun, I think you're probably going to have another dart gun. I'll probably give you a dart gun problem on the test. I haven't written it yet, but it'll be a little simpler than this problem. So keep that in mind. There'll be a roller coaster problem. There definitely will be a magical roller coaster problem where the roller coaster might be at a certain height, and you have to figure out how fast they're going at the bottom, how fast they're going at this top, how much they would compress the spring. Or maybe I'll give you a compressed spring, and you have to figure out how much energy and then, you know, how high up this thing can go. Here we've got a net force that's being applied to an object. Here's the graph of the net force as a function of position. So you'll know that this is the work done by the net force, and then is the area. And if you know the work done by the net force, you can find the change of kinetic energy and so on. So study this problem. There'll be a problem where somebody's where there is a non-conservative force. In this case, it's the friction of the person going down the slide. So you'll have to figure out, you know, how much, what was the change in mechanical energy, and therefore what was the work done by the non-conservative force. And then we have a problem where it's going to involve power. This is a pretty tricky one. I don't think I'll give you one that's, although it's really not that bad, but where something will be putting out a certain amount of power over a period of time, and you might have to figure out how much energy it used, or what's the speed that it can lift something if I give you a certain amount of power, and that sort of thing. So you will have a power problem. There's only going to be 5 problems on the test, so probably, and I don't know which ones yet, you know, I might take 2 of these problems and kind of combine them into a simpler version that covers both ideas. So study these problems thoroughly, and also the starter problems. Study those, and then make sure that you've got all of these, and you should be all right. Okay. I'm not going to try to crush your soul or anything with energy, but just be ready. Okay. Any questions? Oh, one thing, you know what, now that I think about it, we have this thing called internal energy or thermal energy. Remember, if you have, you know, friction that heats up the environment, or if you have something where sound is given off or whatever, that's energy being dispersed into the environment. So, and that's adding to the thermal energy of the environment, or the object itself if it heats up. But then you're turning mechanical energy into thermal or internal energy. Okay. Any questions? Okay. I think you're going to kick it. All right. That is all.